bringing our results forward from the previous board in the previous video. We know that the initial velocity in the second ramp then is equal to the final velocity in the first, which is given by this expression. I'm not going to read it to you. We know what it is. The final velocity on the second ramp is 0, from which we follow our flow diagram or follow our reasoning in whatever way. We put these together, we determine the average velocity to be the sum of these two divided by 2, which is just going to be 1/2 of that square root. The change in velocity on the second ramp, well, we start off here, we end up here, the change will be the negative of this. We subtract the initial from the final. We end up with a negative square root of the same expression. Now, the acceleration on the second ramp is the change in velocity divided by the change in time on the second ramp. So that the time interval on the second ramp is easily calculated as the change in velocity divided by the acceleration, which will be the negative of this square root times the negative s2g, which is the acceleration on the second ramp. Now the delta x2, the displacement on the second ramp then, is going to be the average velocity times the delta t. Okay, the average velocity is this expression with the square root. The delta t is this expression with the square root. Now, I'm not exactly tired of writing everything under the square root sign, but for the purpose of brevity, I'm just writing square root dot 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 square root dot dot dot, because every square root on the board is going to be the square root of the same expression. So the average velocity is 1/2 the square root, as we see wherever I wrote it here. And the delta t is the negative of the square root over negative s2g, negative s2g being the acceleration on the second ramp. So we have that expression here. Multiplying them together, kind of left off something here, but okay, get it right. We have 1/2 the square root times the negative square root divided by negative s2g. Two negatives will give us a positive. Square root times the square root is the square of whatever's in the square root, and we end up with 2 s2g in the denominator. So I want you to pause for a second and write down your expression for delta x2. Okay, presumably you've done that. I want you to now pause for a second and write down what your expression will be if, as in the current example, v1 naught is 0. Okay, hopefully you've written that down. Now you might ask why we didn't substitute 0 in for v1 naught in the first place. Well, you know, we might have a situation where we start the ball from some velocity other than 0. And we could certainly analyze the motion on the first ramp under that condition, and this is the result we would get for the final velocity in the first ramp, which would be equal to the initial velocity in the second. So that the expression that we get, delta x2 equals v1 naught squared plus 2 s1g x1 naught divided by your 2 s2g works for any object that starts in the first ramp with at position x1 0 above the interface and with velocity v1 0. Now, and let me back up and say this expression does simplify. We could divide the v1 0 squared by this expression, the 2s2g, and divide this by the 2s2g. When we divide this by the 2s2g, we just get s1 over s2 times x1 naught, which is kind of interesting, and that's going to be very relevant to what we see when we do this experiment with the two ramps. So v1 naught is 0. That implies delta x2, this term's no longer there. We divide this term by this term, the 2g goes out, and we can write the result as s1 over s2 multiplied by x1 0. Now, what's the interpretation of this expression? S1 over S2 times X1, 0. You should think about that interpretation before I go on. So you should pause and think about what that means in terms of the two ramps. We've got a ramp here with one slope. We've got a ramp here with another slope. We start a ball here. Where does it end up here? S1 and S2 are the two slopes. How do the two slopes influence the final position of the ball? If you can figure that out on your own, figure that out yourself, you're going to be way ahead. And I'm actually going to just stop this video here, and I'm not going to go on in this particular video. I'll go on in the next video, and hopefully you'll have an opportunity to think about that in terms of what you've seen.